This video is going to cover sections 3.5 through 3.7 of your textbook, and it will cover input and output to data files, error handling when you're working with data files, and a little bit more on the use of the break statement. So engineering problems often involve a large amount of data that is stored in a file, and you can either make data and write it to a file, or you can get the data from the file and have to process it in some way. So my little example down here is showing data that's the total solar energy from the sun. This is measured from a satellite that's up above the Earth. This data goes from January in 2004 up to the present. So it's a very large amount of data. However, you can, in this website, which is from I think it's the University of Colorado Boulder, but you can, from this website, limit the data to some smaller subset that you want to see. So for example, here is this total solar irradiance coming from the sun this year, so starting January 1, 2015 up into the present. So you can see that we have a cyclical behavior. Sometimes there's more total energy from the sun and sometimes there's less. So it's cyclical on a monthly basis, actually. So you should probably be able to count out 9 or so months right here. I can download this data by clicking down here, and I've already downloaded the data so you can see what it looks like. So make it a little bit bigger. So this is the data, what it looks like. There's some header information on top of this text file, and then this is the date. It's a Julian date, and this is actually the radiance measurement in watts per meter squared. And so it's a very large data file, but you could process it and you could do some analysis on it. So this date right here, this is called a Julian date, and you can actually go to a little converter and figure out what that Julian date is. Let me do this date. I'll do the date right there. So that's the first one on the data file that I see. So compute the calendar date. And I don't know if you can read it, but it actually says that it's January 1st of this year. So that's the Julian date. So large amounts of data. Scientists and engineers want to look at the data, process the data, import it into their programs, compute things from it. So that's what we're going to learn about. Anyhow, put that down. So the process, which will become clear as I go through the example, the steps for our programs to read from a file or write to a file, data file, is listed right here. So our data files can be several different formats, but they're often a .txt or a text file, which means that Notepad opens it up. It also means that Notepad++ will open up these files, but by default, usually Notepad opens it up. There is another type of file called a CSV file, which is a comma-separated CSV. I suddenly forgot. It's a comma-separated file, so all your data is separated by commas, and I'll give you an example of that. So our steps are, in general, that we have to make a declaration and declare a data type that's called file. More on the next slide. Then you have to, after you've made a declaration, you have to associate your declaration with the file that's somewhere in memory on your computer, either the file you want to read to or write from. Read from or write to. And then the next process is to actually read the data one line at a time, or write your data one line at a time, and then in the end you have to close a file. And there's an optional preprocessor directive that we can use to make it life easy. So sounds like Greek right now, so let's continue on and see what these steps really mean. So our example that we're going to use is we are going to read some data. It's actually seismic data that's taken over time, and we want to find the average of the data and find the maximum and find the minimum. So here's an example of what the data looks like. I can actually show it to you for real here. So there it is, opened in There it is, opened in Notepad. So that's what automatically opens up. On my computer, it's a text file, and it says text document over here. Here it is bigger so you can see it. So the file looks like this when I open it up in Notepad. There is the first line just says 10, and it happens to be the number of data points in this file. And then the next two columns are, this is time, and this is the amplitude of the seismic measurement. Whatever, the units aren't there, it's just the data, it's the raw data. So for you to write a program to read this data in, you have to have a knowledge of what the data file looks like. So I have here that a priori knowledge of the data file format is required. So you can decide how to handle the data. Actually, when you read in data, it's called parsing the data. So, steps in the program. So the first thing, that's the example that we're going to use. So the very first step is that you have to declare a file data type, and it will have to have a pointer identification. Again, this sounds like Greek, so let's look at my example down here. You're used to making declarations. Here's a declaration where I've declared a data type double, and I'm using identifiers of time, motion, sum, max, and min. So these names of variables essentially, are called identifiers, but this identifier is really reserving a place in memory where we can put our data from the program. That's how it works. It's just the name of a place in memory, and it makes it more human readable for us. I can put 0 in my place in memory that I've given the name sum, and so I've already filled up some value in that place in memory. So this is in our declaration area, and we're used to declaring ints and double data types. So another data type that you can declare is a file data type. It's slightly different, but we're making this declaration that we're going to use a file in our program, and we're going to give it the identifier of asterisk sensor. So the asterisk means that this identifier, in other words, a name of something, is a pointer. So next slide we'll talk about what is a pointer. And when you make this declaration for a file data type, you have to use the capital word file. That is because in the standard I/O header file, that's how it's defined in that file. So it must be capitalized, and it must be the word file for that declaration, as opposed to when we declare our ints, doubles, floats, whatever we're declaring, they are lowercase letters. That's also defined in the header file standard I/O that you put in your include statements at the beginning of the program. Okay, so you're used to making declarations of things that you're going to use in your program. The difference here is that when you declare a file data type, you have to have a pointer as the identifier, and the way you designate that as a pointer is to put an asterisk in front of it. So what does that mean? What is a pointer? A pointer is a variable, which is like an identifier, that can store an address. So you have to remember that, like I was saying in the previous slide, every piece of data is stored somewhere in memory on your computer. And in this example from the previous slide, we have a place in memory that we're going to call sum, and we're going to store a 0 there. The actual place in memory will be different on different computers. But when you use a file, your file is stored somewhere specifically in memory. It is at a specific memory location. So I can't run the program every single time and use a different memory location, like when I declare doubles. When I run the program and I have a file involved, there is a very specific memory location involved. So this pointer is really an address. Right now I'm saying I'm going to have an address, I'm going to give it the name sensor, but this address has to be somehow tied to where that specific file is in memory. So I've declared that I'm going to use a file. That file is going to have a specific place in memory, and that's what the use of a pointer is. So this is a convenience up here, which I'll talk about in a moment. So continuing, I'm growing this program right now. I've declared made some declarations at the beginning of the program. I will need an integer number of data points and a k. I will need a double data type, time, motion, sum, max and min for this program. Remember the premise of our program, we're going to read this seismic data and find max and min. Oh, and that data must have been motion and not amplitude. I think it's the amplitude of the motion. And I need a data type file, and we're creating that. We're going to have a pointer to that file. So when do you actually assign the location and memory where the file is? I have to actually assign it and point to it by my program. My program has to find where that file name is, and that file name has some address associated with it. So I'm going to open the file. Actually, I'm going to open sensor1.txt. That was my data file. So I'm going to open sensor1.txt, and I'm going to open it to read. And I have this optional preprocessor directive which makes life easier by saying I'm going to define a constant named a file name, and this is what it is. So you're used to using define, like define pi or define any other constant. This time I'm going to define file name, and it's going to be this file name right here. That's because later on it's easier to change the top of your program, what file I'm working with at the top of your program, than somehow down inside your program. So this is just a convenient step. So anyway, I'm going to use this file open command. It opens a specific file name. In this case, it's going to be sensor1.txt, and it says what I can do with the file by putting this file status at the end. I can read to the file, write to the file, or append to the file. So I want to open something, and I want to read the file. Now at this point, the address of the file has been stored in sensor. This data type, file data type, which is a pointer. Sensor will have the address of the file right now, so the program can find the file and work with the file. So you can read to a file, write to a file, append to the file. Here's a listing of actually all the options you can do when you do a file open command. So you either read, or you write, or you append. And you can also append by overwriting your data. So what if your program can't find the file? What if your file is in a different directory from where your program is? In that case, you would get an error message. So when you do this file open command right here, this file open, when you do it, you either get back the address of where the file is located and store it in sensor, or you don't find the file and you get an error. When you don't find the file and you get an error, null is returned to sensor. So sensor gets assigned the value of null, which is a keyword in the C language. If you don't want that to happen, make sure you put your data file in the same name, in the same directory as your program file, or else put your path to the file as a complete address. So how do you handle it if your program doesn't find the file? Here's an example. Here's a good way to handle it. So you say if whatever gets returned to sensor is null, meaning we didn't actually get an address and we got a null because you couldn't find the file, then you're going to print a statement to the user, error opening the file. However, if you got an address, I have an else statement. If I got an address, I'm going to start scanning the data in from the file. I'm going to import the data from the file into my program. So remember what our data file looks like. I said you had to have a priori knowledge of what the data file looks like. The very first line of data is the number of data points. It is one value on that line, number of data points. So my first fscanf command is to read that first value. So I read in that first value, and I store it in my variable with the identifier number of data points. So I read fscanf is a file scanf. It's not a scanf by itself. You're doing a scan from the file. It reads one line at a time. So I'm reading one line at a time from what's happening at the address stored in sensor, where the data file is. I'm going to get that one line. I have to match the data type right here. And then I'm going to store it in this variable called number of data points with the identifier number of data points. But what does my next line of code look like? My next 10 lines of code have a time and a seismic motion amplitude number. So I'm going to need to use fscanf again to read the next line. Now what you don't want to do is write fscanf 10 times and read in the 10 lines of data. If you do that on your program, you will get severely marked down in the grading process. So you should not have repeated code like fscanf 10 times. What you need to use is a loop. A loop makes your program efficient. So let's do that. So I have a fscanf. I read the first line of data in, which is a single data point, and I put it in number of data points. Now I want to read the rest of the file. A for loop is very appropriate for this. So here's my initialization of the loop at k equals 1, and for k less than or equal to the total number of data points, which is 10. Then I'm going to do what's in the loop. I'm going to come back and check. After one pass of the loop, I'm going to come back and check, is k less than or equal to the number of data points? No. I'll go back and do I will update the value of k. I will go back and repeat through the loop until k finally equals 10. Then I will no longer increment k, and my loop will be done, and I will proceed with the execution of the rest of the program that's past this for loop. So what happens with the fscanf? I enter the loop the first time. I read from the address pointed to by sensor, and I read 2 values in. Because why? There are 2 values on this particular line in the file. I'm going to store the first value in time, and I'm going to save the second value in a variable called motion. And then let's look at what's happening in the loop. First pass through the loop, I say if k is 1, then the maximum value equals the minimum value equals the motion value. Remember, we have to find the maximum value of this file. And then sum gets whatever this value, sum actually gets the value of the first motion value. I think it was 132. Sum gets 132.5. Shows right there. Now I do a test. If the current value of motion is greater than the maximum value, then the new maximum value gets this value of motion. If the value of motion is less than the current min, then motion will become the new current minimum. And as I go through this loop, the next time you need to convince yourself of what's happening in this loop. The next time I go through this loop, k is no longer 1, k is 2, and I jump to this if statement. I get the next value of motion, which is 147.2, and I say, is motion greater than max? So 147.2 is greater than the current max, which was 132, so the new maximum is 147. So etc. It goes through the loop 10 times, and it always determines which number is greater, sets it to the max, or which number is the minimum and sets to the minimum value. The rest of the program is just outputting the data, so they're just print statements. Print number of data points, print average reading, there was an average calculation, print max, print min, and then file close. Very important to have the file close statement. The file you just opened and read data from must be closed. If you don't close it, one thing you can do is corrupt your disk. The next thing you can do is the next time you try to do something with that file, the next time you open it, maybe you want to delete it, you're going to get some kind of message that that file is not available. So very important to close your file. So that last example we just did, the file was nice because it said, okay, I have 10 lines in the file of data, and I used that to read in 10 lines of data. But there are two other ways you could have done this. The first one we did was by a specified number of records. Each line is a record. Alternatively, we could have used a special signal at the end of the file called a trailer signal or a sentinel signal, and you look for that signal at the end of the file to say that that's the end of the file. So here's that example right here. All my time data is positive, but if all of a sudden time was negative 99, then you would know I could test for that, and you would know I was at the end of the file. The third example is an end of file indicator. It turns out that all of these files have a hidden end of line. An end of line marker, if you will, and you can also test for end of line. So let's show you these other two examples. So here's the example with the trailer signal. Remember, I had a minus 99 as my last row of data, or my last record. It's also called a record. So the program reads in data the same as before, but I have a different structure here. Instead of the for loop, I have a do while loop. So I go through, I do the same, finding the max, finding the min, finding a number of data points, but I only do it while time is greater than or equal to 0. So the moment I get to this record, this last line of the file, and time is less than 0 because it's minus 99, then I'm done with the do loop. The last method, which is the one I like the best in many ways, is the end of file indicator. So again, you still have to know something about the file. You don't have to know if it's 1,000 points or 2,000 points, but I know that in this data record that I have 2 columns of data, and every time I scan in one line of data, I read two values of data and store it into 2 different variables. So my fscanf function is expecting to read 2 values at a time from each line of data. If you do not read 2 lines of data, then you will get a null. But I can do a test. While I successfully read 2 lines of data, so while the result of fscanf is 2, because I've 2 values of data, so while that evaluates to 2 and that becomes a true statement, then I will continue executing the loop. The moment I do a fscanf and I don't get 2 values to read, then I get a false and my while loop is done. This is the method I like the best. So when you write data to a file now, it's a very similar process. It's very similar to reading. But the difference is you must decide what your data file looks like. Is it 2 columns of data? Is it 4 columns of data? You have to decide in advance what your data file is going to look like. And then you also have to decide how you're going to identify things in the file. Do you need a trailer to indicate the end of the file? Do you need the first line of the file to be something informative, like how many lines of code there are, or the date where the data was taken? You can have lots of informative lines first. And then finally you have to decide how many columns and what format the data should be. Is it integers? Is it doubles? What is it? So you have to decide all of that before you can write the program. And again, you have some knowledge then of what your data looks like and or what it's going to look like, and you're going to write it to a file. So here's my example. Write a program that determines the value of this function shown below at t equals, you could see there's 100 lines of data, so t equals 0, 0.1, 0.2, all the way up to 9.9 seconds. That's 100 lines of data that you're going to calculate. And then I want you to plot that function using the plotting program of your choice. So this is the function that our program has to implement. It's actually called a damped sine wave. So it's a sine wave that decays over time, and you'll see it here in a moment. Here's the code. Since I'm using sine waves and exponential functions, I better include math. I cut off, sorry, at the top. The include standard I/O is also there. I need pi in this formula, so I'm going to define a pi constant. And just because it's more convenient, I'm going to define a file name called dsine.txt. So I've already made up what I'm going to call the output file. And when the program executes, it will create that output file. So writing to a file, again, I have to make a declaration with a pointer, and my pointer, I'm going to give it the name data out. So now I'm going to open that file, create that file. So data out equals file open, and I'm going to give it the file name up here, dsine.txt, and it's a file for write. This file, the actions you can take on this file is to write. So I can write to dsine.txt. I have associated dsine.txt with an address pointed to by data out. So I'm going to need 100 data points. Let's look back at the function for a minute. Let me get the function so you can refer back to it. Okay, so there's the function so we can refer back to what's happening. So I need t to go from 0, 0.1, 0.2, 0.3, 0.4, etc. So this is what that calculation does. T equals 0.1, just the increment, times k minus 1. So when k is 1, t is 0. When k is 2, t is 0.1. When k is 3, t is 0.2. K is 4, t is 0.5. So you get the pattern here. So that's how I'm creating my column of time numbers that I want to calculate this function at. Function has got to be calculated at t equals 0, 0.1, 0.2, 0.3. I could have also started with k equals 0 and not had the k minus 1, but then I would also have to make sure that this test that I do was correct. So there are a couple ways you could do that. Then I compute the function. So f, I called it f equals, there's the function written out that implements this. And then I want to print to the file, so each line that I print, I use an fprintf. I'm going to print to data out. Data out is an address. I'm going to print to that address, but I've already associated it with a file named dsine.txt, and I'm going to print one data point, which is time, see time, and I'm going to put the next data point in there with three digits past the decimal point will be the value of the function. So each pass through this for loop, time will get incremented. I'll compute the value of the function, and I'll print out 2 data values per line in the file, and then I must not forget to close the file in the end. So let me show you what it looks like. There I actually have a different program up, sorry. So this is the program that I implemented. When I ran the program, you don't need to watch me compile, but it will compile. When I run the program, it creates a file. Oops, sorry. Clicked the wrong place. Classes EE160 Programs, Chapter 3. Okay, so when I run the program, it created a file called dsign.txt. I don't know if you can see it, but there it is right there, dsign.txt. I double click it, it opens. There's my data. It's not very pretty. At time 0, I get this value. At time 0.1, I get this value. It's kind of messy looking in Notepad. It didn't make nice columns, but the data is definitely there. So that turns out to be a little bit of an issue, and I wasn't sure that everything was right. So instead I opened it in Notepad. And it certainly looks prettier in Notepad. I can see all my time in a column, and here's all my values of the function in the second column. So it indeed worked correctly. So I was happy with that. And then I said, plot. I asked you to plot the data in the program of your choice. So you can do MATLAB, you can do Excel. Most people have Excel, or the Google version of Excel, which I don't remember what theirs is called. So I'm in Excel right now. I'm going to create a blank workbook. Data. I'm using Excel 2013. It could be a little bit different. You can also just open the text file. It will be similar. 2013 has an option for importing from a text file, so that's what I'll do. Get data from text. Here it is, dsign.txt. I import it. And whatever version of Excel you're using, you'll get some kind of an import wizard window that looks exactly the same as this. You get a preview of your data down below. Delimited means that the data on each row is separated by something like commas or tabs or spaces. So there's a preview of my data. I want to see column lines there, so I knew my data was actually separated by a space. See, time is separated here, so I'm going to put space, and then I will finish. Put the data there. Finish. Say OK. And so all my data is here. I have time in one column, and the value of the function in another column. Let's see if I can fix that view a little bit. I want to zoom in. Okay, now you can see it better. So it imported, there's time in one column, the data in another column, and I said plot it in the program of your choice, so I'm plotting it in Excel. How do you do a plot in Excel or Google's equivalent of Excel? Generally you're going to insert a chart of some type, so I did insert. I'm going to use, here's my chart types. I'm going to use what's called a XY scatter chart because I have X values, T values, and F of T values, which is like having XY values. So I'm going to do that. I think I want to see the data points individually. So this says connect the dots with curvy line, connect the dots and don't show the dots, but I'm going to connect the dots. I'm just going to show the dots. I'm going to show the data points. So now I have to put the data on. That's a select data. Add. I'm going to call this, it's a damped sine. Damped sine wave. get my X values. In Excel you can just select all your X values. I selected my X values. This says series Y values. I'm going to now select all my Y values. Doesn't matter which order, there's all my Y values. And okay, so there's the plot. That's what the data actually looks like. And I said, ooh, that's a little messy, so I think that I will format the data series. There's some options. I want to convert it to being connected dots so you can see it a little bit better. I know there's a way in Excel. Yeah, there we go. I want to see it like this. So now I've connected the dots and you can see it's a sine wave, and it's called a damp sine wave because it just decays. So waves, all kinds of waves do this. Waves decay. So anyway, so I've now plotted it in the program of my choice. If you need help with plotting in a program of your choice, let me know. I will be glad to help you. Join the Google Hangouts on Tuesdays and Thursdays, or let me know a better time for you, and I will be glad to show you other options. So anyway, so the program in the end made my time values, evaluated the function, and plotted it all out to a file. And after that I had the data file, which was called dsine.txt, and I opened it in Excel and I plotted what the data looks like. So next other thought I want to show you here before going, I have a for loop to read in the lines of data, but before I can use this for loop I had to make a declaration for the variables of the for loop, which is a k. So I made a declaration up above int k, and then I entered the for. When I went to the for loop, k was defined, it was declared already, and I could run my for loop. There's an alternative to that notation. I can not even define int k in the declarations, so I have it commented out here, and then when I go into the for loop I say int k equals 1. So I make the variable declaration right here in the for loop's argument. Because k is just an iterator, it's not anything else. It doesn't have any other meaning in this program, and I only use k within this loop. I don't use k anywhere else in the program. So it's convenient to say int k equals 1, and k is just this local iterator within the for loop. If you choose this notation, which I like this notation, when you compile the program you will have to put an additional option on your compile statement. So my program was called write example, or write ex right there, and I went to compile it, gcc, the usual, write example.c, make object file, the executable is called write example, but I put an additional option on the end. So all options start with a little dash name, like right here is an example. I put an additional option on the end that standard equals GNU 99, and when I do that I'm allowed to have this additional feature of making a declaration within the for loop's argument. So it's nice because k isn't useful anywhere in the program except as an iterator, and it makes your for loop keep k local, and it's efficient. So, but you just have to compile with this additional option on the end for using this process. Okay, that's what I have. I want to show one more thing. It's come to my attention that not everybody is aware of where you find, actually I'm going to show you two more things, where you find how I've graded your homework. So I am going to show that to you now, just in case you don't know where it is. Let me fit in my window here. So go to Laulima, sign in to Laulima. Now your view will look a little different than mine because I have the instructor view, and if I turn on the student view, then I can't look at the students anymore, but the students view anymore, except to test my programs. So we're in EE160. And if I go down to tests and quizzes, where I make you submit your homework, just because I like the tests and quizzes options better than using assignments and tests. Tests and quizzes lets me do more things than assignments and tests does, so I use tests and quizzes for your homework submissions. So I'm going to go over here to where your assignment was. I will go back and look at one of the early ones. Let's do this one. Oh, you're not supposed to see everybody's grades. But I'm going to flash this so you can't read everybody's grades, and I'm going to borrow one of my students here. I'm going to borrow. So this is the view you should get when you go back and see your graded assignment. You should see, for example, what you missed on a question, and then whether there will be something attached at the bottom when it's graded. After you've uploaded a program, I grade your program and I submit an evaluation. So look after your program. You could see that there could be some comments for you. This comment was see attached, but there's an attached evaluation. And so the evaluation shows how I graded, and it will have comments about what you did wrong, where you lost points. Sometimes I snapshot your code and stick it in here down below, and then you can see how you were graded. So be sure to look for that evaluation document that's attached to where you submitted your homework. So I think I had one more thing to say. What was my one? Oh yes, one more thing is that back here on the resources folder, I added a new resource, this C reference card. The C reference card is a very convenient reference for everything related to C. You should download it and use it, but let me show you some of the features it has. For example, all of the different kinds of preprocessor statements that you could use are listed here. So we had our includes and we've used our defines. You can actually use conditional statements in the preprocessor, but we're not there yet. So preprocessor statements there. Here's a list of all the different data types that we could have in the declaration statement. Here's what's included in standard I/O, standard in, standard out, standard error. Here's some file I/O information. So here I said that when you declare a file, it's file and then star whatever the file pointer is. Talks about file open, writing to a file, reading to a file, and some more that we'll learn about later. We used file close today. So file close operates on an address. File scan, fscanf operates on an address. What else do you get? A list of all of the mathematical functions in the math.h header. So here's the last list of the mathematical functions. There will be some time and date functions coming up that we can use. What do you get in the standard library? You get some other functions in here. We will use rand for random number generator in the next chapter. Integer type limits. So anyway, nice reference located. I put it in the resource folder for you. Here's a list of all of the standard libraries that we could be using, including standard I/O. Your homework problem today is going to use some character tests, which was the end of chapter 2. So converting to upper and lower case on characters. Here's our flow constructions, if, while, for, do, and switch. And it has the format there for you. So it's a very nice reference, and it's located on in your resource folder in Laulima. Also, the evaluation document that I'm using to grade you is listed there if you need to refer back to it. Okay, that's what I have for today.